Okay, good morning. Today we discuss about the first experiment half-wave dipole antenna radiation pattern. So this is the half-wave dipole antenna. This is for quarter-wave dipole antenna. This one for half-wave dipole antenna. We are using this quarter-wave dipole antenna for receiving purpose. This one for transmission purpose. And just you see already, sir, it will be explained what are the component it will be present here. So everything already you know. So
as in the previous video you have seen the different portion of the component which we have used. As sir shown just now, this quarter wave dipole antenna, and we want to know the radiation pattern. And you know, radiation pattern is what? It's a plot of the radiation, or we can say radiation intensity. It may be field or power with respect to an angle of theta phi. Because we are taking the radiation in a 2D plot only, so you can see specifically that both the antenna heights are same. So what we'll do is we'll rotate in only one direction, theta direction, and we'll see by rotation the theta direction what are the radiation pattern changing. So in a practical aspect, if we say a quarter wave dipole antenna, we want to know the radiation pattern of this, and generally we take reference half wave dipole antenna to transmitting side. For this case, you need to connect the transmitter to the RF generator as we do, and there is an alignment important part. The radiation pattern alignment means what? It is a relative value of the pattern which we receive from a transmitting antenna. If a radiations are because of the RF signal, time varying signal, which is creating the current flowing in the antenna, radiations are going to exist. So this region is what? It's a free space region. From this part to this part, we can say it's a free space region. So that is the radiation. You can put your hand and you can find the difference here, because the detector is already there with us. So we can see what is the radiation coming. Currently no antenna is there. Supply is on. The radiation, we have given the RF signal to this. Now nothing is received because there is no modified structure. Metallic structure is there, and modified metallic structure is an antenna. So starting with this, we are taking this time the antenna of quarter wave and half wave antenna. With this, when we see the far field pattern, we must have a value which is faithful value with first we adjust to, and that is called as an alignment. It means when you are connecting a transmitting antenna, half wave dipole.
Yes. So here, just you see here one knob will be there. Just you connect here. So this is a half-wave dipole antenna connection here, and first of all if you measure the transmitting antenna height, and also similarly the receiving antenna height also it will be measured, and also it will be connected to the any one half-wave dipole antenna or otherwise quarter-wave dipole antenna. So here the distance between the transmitter and the receiver, first of all if you measure. And one more thing, both antenna in same direction also it will be placed here.
Then the purpose of this to keep them in the same direction is because when you are keeping the distance between them, it should be in the far field, because you know in the near field antenna, when antenna radiate in this region, the electromagnetic doesn't radiate. Actually, electro and magnetic field are perpendicular, orthogonal, but they do not propagate. Reason being, in this region they are perpendicular but they are out of phase. After a certain distance, which we understand in theory called as a limit of near field and far field, 0.62 times of root dq by lambda. Dq is the most linear dimension. It means the maximum linear dimension of antenna. So with this dimension, if we say you take this d, and if you calculate 0.63 times of root dq by lambda for the frequency which we are using, that much distance should be there. After that only far field pattern will be received. Okay, that will show when we keep it closer that no radiation will be there. If we keep it very close, we don't find the radiation is there. Either it should be connected, otherwise it should be away. So there is a compromise between this length. You can say near field, far field. So near radiative field can be there, near reactive field radiation cannot exist. In near reactive field to far field region boundary, this antenna is placed. So this is the distance between them which is placed, and now we have connected one antenna here So first thing is to align, like when it is in the line of sight. For example, me and Professor Perumal, we both are standing in front of him, and suppose we both are speaking. Okay, if you consider the acoustic signal which is going away, or we can say it is transmitted from me to him, the similar height should be there. It should be in line of sight, and then it should be adjusted that when he can maximum listen me, he will listen to me maximum when he is exactly facing to me. So in the same way, these two antennas are facing each other, and we have to adjust, because it's a relative value, what is transmitted from here and what is received signal here, it should be faithful. For example, if you are giving suppose 100 microampere of current which is flowing from this RF antenna, and suppose the received signal is very low of here in the RF detector is detecting the value, for example 4 microampere. That value is not going to help. Let me show you here. With the RF value, with this full adjust and this label, we adjust first, because we have not started taking the pattern yet. We have just aligned now currently this antenna in the line of sight facing to a quarter wave dipole. This is quarter wave dipole antenna whose radiation pattern we are checking, because it is receiver is here, and here transmitter antenna is there. We will rotate. Reciprocity it will follow, so we can rotate in this turntable this one. So at different angle, what is the value coming, we are going to note down. But note this down, that what value we are giving here. Let me reduce this value, full scale adjust value down. We are taking output from either RF generator or output from here, doesn't matter. So because it's we are not using external input currently. So from here, when we give input here, from this side the radiations are generated and radiations are received here. What is currently you can see in the RF generator is, if I reduce the increase the distance, can you see? I am not changing anything. The RF generator value, it means the antenna transmitter is transmitting a certain value here, and the received value here is 42, little bit fluctuating. It will be fluctuating. It also affects because it's a low electromagnetic signal. So if I put my hand in between, can you see sudden changes? My hand is in between. It is coming. You can see RF detector. I am keeping, again see, the antenna transmitter is at 89.5 microampere. It is displaying. That is transmitted from this. The current which is going to converted by this transducer, it means this antenna, into the radiation, and these radiations are going to be received by this. If an obstacle come in between this, you can see there is a reduction in the detected value. If it is not there, you can see, if you keep a little silent and see, almost it is stationary up to 44 point something, right? So we applied here 89 and we received at 45. We can still consider it as a faithful. Reason sorry, the reason is this is faithful because 50% of the output is still available, and it's the electric field. So when we'll take power out of this, we'll take E square field pattern, we'll take as E square by the impedance of the transmission line. Okay, eta z and eta z, eta naught. So because of that, we can say it is faithful when it is line of sight. So it is ideal to start or rotation. So don't suddenly just connect the transmitting and receiving antenna before adjusting the gain alignment. Don't start the experiment. See, at least the 50% of the output is available. Here 89 is there. If it is not there, there is a alignment capacitor, gang capacitor is available in the antenna trainer, which actually fixes the value of it can help you to increase the RF detector value there. We can adjust this. So you can say we have adjusted it to maximum, then after it was reducing. So it is called as an alignment. So a relative value, if 89 is there, so first we have adjusted this, that 89 something is the input, we can keep it to 100 also. For ideal case, I am keeping it to somewhere 100 microampere current is there, so it will be easy for calculation. Almost around 100.7, and here you can say a receiver here is showing the value of 46. Okay, so with this value it is ideal I can start with my experiment. So now sir, please take the every 10 degree angle of this. We start, because you can see currently it's showing 90. We can also adjust this. This is a masked, so from this we can adjust, or still it is a 0 degree. Let me adjust exactly. that at 0 degree we have adjusted it, and we note down this at transmitted power, right? So let me note down the power from the transmitter is 100.7. We are writing in terms of current, so we can say it's a transmitting current IT is 100.7 microampere. Okay. Now at that point when we adjusted or we aligned, it is showing the maximum value around 52 point, just a minute, 50, around 50 it is there. So we can say 50 microampere of current is received when it is at 0 degree. Okay. So with this input, when we are telling, we are not going to change now the RF transmitter. We are going to rotate transmitter only. We are not going to change the value from the antenna trainer. From this trainer, we are not going to change the value. So with this, the transmitted current is going to be fixed, and the received current at every angle, so it is going to be 100 microampere. We can say 100 microampere current. It is going to be same for all the cases, and here the current at 0 degree, 10 degree, because we can say there is a span, even we can go for 5 refined value 5 degree also, but easier is because we are taking manually, so we can take 10, 20 degree, 30 degree, 40 degree, what are the values are there, we are going to observe and going to note down. Okay. The later cases we can convert that into dB and display it. So let's see with this. Sir is rotating it for every 10 degree angle now. It is from 0.
First of all, 0 degree, what is the output it will become? Approximately, sir, it will be not on 50 microamps. Next, we will rotate the, how much here, 10 degree. Just I will change 10 degree means, what is the output it will become here? Just you see, for approximately
38.3.
That second one, 38.3. Next
3 microampere. The current values are in microampere.
Microampere. Okay. Then it will be changed. Here 0 degree, then 10 degree. Next it will be changed 20 degree. What is the output it will be? 20 degree means just you see the transmitting antenna and the receiving antenna, the direction it will be slightly, it will be changing. 10 degree or 20
So it is
degree.
adjusted to 20 now.
Here.
We may need to make sure that we are not creating any obstacle, otherwise you will not be able to record the value. So there should be no obstacle in between them. After adjusting it to 20 degree, it is showing some 45.2 around. If suddenly we actually our hand comes or something, some changes we do, we will see the changes in the RF detector. It's a very sensitive meter because actually it is radiations are not given by any source. Actually it is radiated from this source and it is received. So that's why it is indicating detecting the value of RF signal here. So by any means, by any obstacle, by a fan noise also you can find some fluctuation will be there. To get the exact reading, just calm down, wait.
So initially you check the transmitting antenna and the receiving antenna, both are in same direction only means.
So you can see 35. Can you see that we are away, and let's wait for 2 minutes. See, we created silence. We are not moving around nearby this setup. So you can see it is around 37, it stopped. But if we come closer and we do other work, you can see fluctuations will be there. So take care while you do the experiment that once aligned and once settle at 1 degree, wait for this to stabilize and note down the reading, right? So
next it will be changed
30.
Okay.
You can see it stabilized at 31.3 degree. 40.
Next it will be changed 40 degree.
$21.2.
Next it will be changed 50.
I think you understand that why we are keeping away and waiting for the display to stabilize. Reason being,
just you see the transmitting antenna not in line of sight. The transmitting antenna, it will be rotating somewhere, and the receiving antenna, it will be stable.
So 50°, it is 12.8.
Then 60°.
It's around 5.4. Sir, you can go for 20° change, please. Next to this, 80. Go to 80. See how closely we take it is a 10-10°, then it will be, we'll get a refined value, much closer value. If you want an approximation of a radiation pattern, we can go for 20-20° also, 30° also, because we have to cover this all 2D pattern, from 0 to all to 360°. So we need to we see when it stabilizes, you can see here at 80°, it is 0.03. Yeah, 0.3 only. It is 0.3 microampere at 80°. Can you keep it 90°, sir, please? 90. It is 4.7 at 90°. You can see a wide difference between 80° and 90°. Now go for the another 30° change, sir. 120. So dear students, you can understand that we need to stabilize it, to wait till stabilize the value 120°. It is 22 point something. I'm taking approximation, but while you take this, we take the readings very carefully.
Now we will change
150, yes sir. So you can set 150°, it's 43 point something, 150°, 46.4 something.
Sir, here it will be changed with the rate.
Oh yeah. Sir, 180° please. It is 52.9. Sir, go the larger 40° ahead. It means 190.
190, yes, sir?
Yes, sir.
Sorry, 190 or 290?
Oh, sorry, 290.
Okay.
It is 1 at 290. It is showing. See, I missed some values, but actually it is similar, so that's why in this video I'm not sure displaying all those values. And if you go finally again to 320, 320, sir. Yes. You can note down that 320, it is 24.5 around. And then finally if we come to 0 and 360 are same, so it should again show the value which was in the beginning, and you can see we adjusted it to the value around 43 point.
Zero degree or 360?
So 0° or 360°, we are getting this value. So now with this, you note this, how we draw the pattern. Okay. We use the polar plot, 2D polar plot pattern for doing this. And this 2D polar plot, it is a concentric circles are there, you can see. You have seen several types of graph, like a semilograph, or we can say, it is a Cartesian plot simply. Sorry, polar plot, not Cartesian plot, where we have the angle versus. So the angle are demarcated at different value, right? So as we took 0 at, in our case 0 as this point, okay, so the actual plot will be like this, because our 0 degree was here, sorry. The actual plot will be like this, because of 0 we considered that transmitting and receiving antennas are 0 degree. I think you can see it clearly. So let me note down roughly the readings, what is it is showing. I need to first make the scales here, so we can say what is the maximum value coming, we can scale it down, and it is the value of current only. So you need to calculate, because everywhere the current was still same, 100 microampere. So divide this value by 100 everywhere, and then you can convert, because it's a current value, so you can convert into dB by 20 log 10 base IT by IR. So with this your value will be converted into dB. So after taking this reading you have to take a you can get the value of in dBs, right? If you don't want to display it in dB, you can even take this value IT by IR. It means the ratio of gain ratio at every point, because this field current measured here is going to demonstrate the power, isn't it? Oh sorry, it should be 10 log, no 20 log, sorry, it is 10 log only, because current relates to the power I square into radiation resistance. So if power we are taking converting into decibel, you know very well that we take 10 log 10 base power transmitted upon power received. So power transmitted is I square T, so the square term will be cancelled. So in that case it will be, yeah, it should be 20, correct, 20 was correct only, sorry for misunderstanding, this 20 only. So with this you will calculate in dB, and then after if you note down all the points at 0, okay, if you say, and if I take this because it was already a constant 100 microampere, so I can also relate it directly with the IR value. So if we do it in the linear graph here, considering that value was varying from 40, you can see 0 degree it was around 43, and again 360 degree it was 43, 43, 45 in between this, because we took for this video the values were not much accurate, maybe some decimal, maybe error. So with this 43 point this, we need to make the scale from center, it is varying from 40 to the value of going up to 0 also, right? So let me remark highest value is coming as 52. Okay, so let me take 55. So we can divide these regions, this radius in a form like this, and if I divide this, because the maximum scale is 55 I want to take, so with the 55 at this point, okay, if I divide it to reach it up to 0 here, so it will be 1 2 3 4 5 6 subsections. So we can say 12 into 6, 10 into 6, 60. Yeah, so we can keep one each section as a 10. That will be okay, 10 or 9 doesn't matter. So let me take as a 10, 20, 30, 40, 50, 60 already reached here. So I think we could take 12 also. 12, 24, 36, 48, 60, no, we need to go down, lower down, sorry. We can keep it as a 9. Yeah, this will be correct. 9, 18, 27, 36, 45, 54. So somewhere around her 55 will reach, and then next is 63 here at the end. With this let me start, right? So each scale is considered like this. So our first concentric circle radius is 9, second is 18, third is 27. Here you can see these points are already marked. So according to this, go to 0 degree. What our reading says, 0 degree is 43 degree. Okay, so at 0 it is 43. It will be around near, can you closely look at this point and this point, 43 at 0. Then we go to 10 degree, 10 degree it is 38.3. So sorry, I considered this as 0. I think this graph should be like this for 0, right? These are the same scale. So it is, we can say 43 is coming here at this point. So at 0 the radiation is, it is showing like this. Then it is showing 10 degree, it is 38 point, so it is going lower down in this 10 degree, you can see it is 10 degree, and it is lower down, it means 38 something. Here 38 will be in this concentric circle here. So I marked at 10 degree this point. Similarly, if you go to 20 degree, 45, it is showing some hike here, 20 degree. Then it is showing 31, it is going little bit down, 30, it means 29, 31 is somewhere here. It should be at this angle. It means you can see at angle I am noting down the point. And similarly, if we have then 21, so it is reducing down. 21 is somewhere around here at this angle. Then it is going to at 90 degrees. Sorry, it was 30 and then it is 40. This is 50. 50 degree. It is going to 12.8, so it is very less value, almost going to 0. And then after it is going to 60 degree, it is showing 5.4. The values are 60 degree, 5.4. It was here somewhere around here, and this 5.4 will be here.
Sir, 60. Yes, sir, yes.
And then after we have 80 degree, we have 0.3, it means almost 0. So it is somewhere around this point, it will go to 0. Then if we go to the next values, you can see it is how it is moving. The next values are 90 degree, 4.6. So 90 degree if we go, it is 0, and 90 degree will be here. So it is 1.4, very low values are there. And then after if we go to 120 degree is here, we get the value of pattern. Now it is increasing only. See 46, 52, then it is decreasing. So 46 is here. So we got the value somewhere here at 120, like this. I'm not showing the exact point. You can take your time and you can organize it. Similarly 46, then it is increasing to some value in the next angle at 50. We took the value random only. 180 it is showing 52 is somewhat here, like this. So if you take all the points together and you join them, you will find a pattern will be determined. Actually we skipped some values. You will find those values will be around here. And then after, if you come down, it will go to 54, 52 at 190, already it reached. And then after, it's going down to 1.7, it is going down. And then after again it will increase, because we missed this value. The pattern values will be, it means like this, somewhere here, and it will match here. So you can say a figure of 8 will be achieved in this case, because we took the random value. So you can see this figure which is coming, the pattern which is coming, it will be a figure of 8 in case of a dipole antenna. So with this, how we can calculate the half power beam width? We know more accurate practical values you can get it if you take the close values of angle here. So if this is, we can say when there is no radiation is there, this point and this point, in between this, what is the angle? This angle is called as beam width between first null, or we can say F and BW. Some books define it this way, F and BW. And in between this, if you see the maximum power which is achievable, so maximum power was coming, which was around 52 point something. If you go, because it's not a dB scale, we this time only directly calculated the current. But if you take the dB scale, in that case you can go to 3 dB down. Otherwise, if you are not taking the 3 dB scale, in that case you can say, actually why we divided it, because you can make a small pattern also into this. You have a bit larger graph. Why not to get the better values? That's why we divided it to highest value of the range, so that we can get a bigger pattern. So this is what the radiation pattern is from center. See the maximum value, either you come 3 dB down, otherwise 0.707 times, because we consider these are normalized value. We consider this 100 and then we receive this thing. So it's a normalized value, it hardly matters that what is the value with this. So you go 0.707 times from the center down. So if it is maximum value is 52, 0.707 times of this you can calculate. That value you go down, take a scale, mark it, where is the intersection of this plot from here to here, match it, in between this what is the angle is called as half power beam width. Is that clear? So I think you enjoyed this experiment with this pattern, with butterfly pattern we got. Similarly, when we change the pattern of antenna, a different type of antenna, we get the different type of radiation pattern, and then we analyze this in this way. Thank you everyone. Thank you. You can again reach to us by email or in WhatsApp in case of any difficulty. We'll also try to upload